Okay. Okay. Welcome everybody for this third lecture of this series. Um, I have some questions from the day two. I'll try to pick up some of the relevant ones. Some are there which have already been discussed in the lecture, so I'll not go into this anyway. So one question was Hariharan. Is Hariharan there? Let me see. No. So I'll wait for the person to be online before I discuss that. And the other relevant question was by Dr. Subrata Sarangi. So he is also not here. Okay. We'll wait for these two people to come before we discuss. Anybody would like to ask anything in the meantime? I'll wait for 2 or 3 minutes further before I start. If there are no other questions, then I will start now. Ajay Kumar asks, can you suggest some book to begin with radiative processes? Okay, I really missed sending my PDF of the slides yesterday, but I will do that today. I had the list of books at the front of this notes or the PDF that I will share. So the most common and the best book that we all teach from is Ribicki and Lightman. It's the most widely used reference for radiative processes. You can also look at the Loop by Longuet from 2011. It's also equally very nice. Okay. Amit Kumar is asking why bodies emit radiation and why bodies absorb radiation. I think we already discussed this. That the radiation inherently is a quantum mechanical transition between two states, and similar for absorption. If you have for that section, then we will do that. So I will not discuss this part further. Okay, so I will begin now before it gets too late. The two questions that are on the Google sheet, I will discuss it at the end of the lecture, perhaps, to see if the other two people join. Okay, so these are the references as I was talking about. Vicky Lightman and the book by Longuet. I'll put the book's Longuet's name here before I send it. Okay, this was lecture 2. It's lecture 3. Fine. Okay, so again, welcome everyone for the third lecture. Today, I look to introduce some of the basics of the radiative processes, especially the expressions of the electromagnetic field for time varying charges, how they appear when the charges are moved, etc., and apply that to understand one particular process, which is called synchrotron radiation. So, to just have a recap of what we have done so far, so we have gone through the basics of understanding the formalism of radiative transfer. We've learned about the definitions of intensity, flux, and emissivity absorption, and then have derived this radiative transfer equation and have uh, understood the various solutions of this equation and what these solutions imply for different limits of the optical depth. Then we have discussed one particular type of thermal radiation, which is the black body radiation, and tried to understand what how the radiation from a black body can be characterized in terms of the frequency and temperature, and how can we define some expressions for its intensity. So we've done that. We've learned about the transition between the several states and the Einstein coefficients and how it is related to the black body expression. We've also derived expressions for the absorption coefficient and emission coefficient in terms of some physical properties of the object while relating that to the Einstein coefficients. And lastly, we've discussed about the nature of emission lines, how the emission lines are affected by different processes. One is quantum mechanical transitions, then is Doppler shifts, and then is conditional broadening. All of these tend to broaden the line profile away from just the central frequency at which transition is taking place. And to model such lines, we've seen that both kinds of processes can contribute. One process gives rise to a Gaussian nature of the distribution of the spectrum, and one gives a Lorentzian. And to model any physical system, we often have to use both the Gaussian and the Lorentzian. So we've stopped till there. So we'll begin the lecture today now. So firstly, what I will try to do is give you some very brief glimpse of the of how what not how to calculate, because I'll not cover that here. This is a long subject. But essentially, what is the nature of the electric and magnetic field for moving charges? As you can understand, accelerating charges gives out radiation. So not you can understand. I'm not sure if it is if you're aware of this. If you're from bachelor's, maybe you're not, or bachelor's or on the technical background. If you're in your master's, then perhaps if you have gone through the first year courses, then you must have gone through these. And of course, if you're on a refresher course, then of course you would know this. But just to state some of the facts, we all, at least at this level that you are in, have studied electrostatics. But charges and everything is not and time dependent, except for when you complete the full Maxwell's equation, I guess. And we learned about how to derive the expressions of electric field and magnetic field for different kinds of charge distributions and current distributions, etc. Now, things become more interesting when you go to time varying quantities. And what we'll be focusing on is the expressions of electric and magnetic field for moving charges. Now, if your charges are accelerated, or if charge is moving at constant velocity, then you are not emitting any radiation. But if charges are moving, but the velocity of the charges is changing, then you have a component of of the electric field that is synonymous with a Poynting flux. So essentially, that means that the accelerating charge is giving out radiation that can travel to large distances. And I will exactly show you now why what I'm talking about. So I'll make it full screen. So this paragraph and then this diagram and everything I've taken from Ribicki Enlightenment, just to give you a source from where you can learn this better. Of course, these are all standard material discussed in standard texts of electrodynamics, like Jackson and many others. But some of the discussion in Ribicki, at least for this part, is important. And let me emphasize why we are doing it. We are doing this because someone's mic is turned on. Let me see. Dr. Subhash. Dr. Kumar, I'm muting you. Yeah. So the reason why we want to understand the evolution of electric and magnetic field from moving charges is in most of the radiative processes or the physical mechanisms that give out radiation, it involves a motion of charges, and the fact that the moving charges give out radiation is what allows us to compute the total power emitted from such systems, and then relate that to the intensity that will be or the emission coefficient of the particular system or the particular region of space. So that's why I go into the extreme fundamentals of understanding the variations of electric and magnetic field for moving charges is essential for understanding any more complex situation that gives rise to different physical processes that produce such radiation. Okay, so I'll just give you this formula directly without deriving it. That if you have a moving charge, suppose the charge is moving with velocity v, and we are representing the v as normalized to c, that is beta equals to v by c, then the electric field of that coming out from the charge can be represented in this form, where you have capital R is the, so this is, suppose this is the point at which you're observing the field. This was the point. This was the point at a previous time. So the charge is moving along this path. This is the current location of the charge. So the distance from the current location to the observing point is smaller. But then the what we are and the emission was emitted by the charge at an earlier time, because the emission would take a finite time to reach the point of observation. The finite time is c times this distance. Okay, so at any given time, we will not be seeing what the chart is doing at that moment of time, because whatever is happening here now will take some time to reach the observer. So what the observer sees is what the chart was doing at an earlier time, or what we call as the retarded time. Okay? So this is essentially an expression for the retarded time. So the full expression of the electric field for a moving charge looks something like this, where all these quantities are computed at the retarded position. The retarded position being the point from which the radiation was emitted, and the radiation takes a finite time, depending on the speed of light, to reach the observer, which is given by this capital R. Okay, you have just to take it as face value. But what is important to note that there are two terms here. One that contains only the velocity without its time derivative or without the acceleration term, and the other that has the acceleration term. Also note that the first term falls off as 1 by r squared. The second term falls off as 1 by r. Now, let us look at a situation. This is exactly what I'm explaining, written down in the notes here. Now, let us look at a situation where the charge is not accelerated. Okay, so in that case, we can just drop off this term. And if the charge is just moving with constant velocity, it is very similar to what at least the radial dependence of the electric field is very similar to what you have from electrostatics, except for this kappa term. Kappa is again 1 minus TR, which is related to the retarded time. I'll not go to the details of that. Again, you can look up Jackson or some other textbook. But let us try to understand the physics of, or the physical implications of all this. Okay, so what you might recall from your studies of Poynting flux, etc., is that the Poynting flux is proportional to E cross B, and the energy is the square of that. So if you just look at the amount of energy being transported, the electric field really falls off very fast. They are very fast over here, okay, because it falls off at 1 by r squared. But for this term, the electric field is falling off as 1 by r. And now the magnetic field is r cross E. So if you just look at the Poynting flux term, so this will be just 1 by r squared. Okay, another r will come from the E term here because of the magnetic field. So Poynting flux is E cross B. And now if you just take the Poynting flux and find out the total amount of energy that is crossing the area is going as 4 by r squared. And the energy due to the Poynting flux is going up when 1 by r squared. The r squares cancel from the numerator denominator. So that means this part gives you a term that is providing an energy output that is going on at a constant pace. So that means the energy or the Poynting energy attributed to the Poynting flux can travel for infinite distances. The electric field, although it is falling off as 1 by r, if you take the total surface, it will also keep on increasing. So that is why this term is related to the radiation field, and the radiation can travel to infinite distances. Whereas this term is related to the near field approximation. So this is better done when you do a multipole approximation of moving charges, and there it is clarified a bit better. Okay, so another interesting thing that I wanted to point out here, this is again related to the moving charges, is what happens exactly when a particle is accelerating. And this is very nicely demonstrated by this cartoon picture that is again given in the wiki. Now, one nice property of this form of the electric field is, so suppose you have a particle that has no acceleration, so you can drop the radiative part of the electric field. So just this term. So if you just look at or just think about the vector here, which is r minus beta, r cap minus beta over here. So this is actually points to this line. And someone's. So at any given point, the electric field always points towards the current location of the particle, which is very fantastic because I just now said that whatever we observe at the observing point is what the particle had emitted at the retarded time or at an earlier time. But just plain out of how the Maxwell's equations are, the final form, the electric field always points to the current location of the particle, which is at the point D. This is just r cap minus beta. So the unit vector minus the unit vector, which gives you the small r vector, as I have given here. So now let us consider a situation where a charge is moving with constant velocity. So the electric field of that constant velocity charge would look what is there on the outer side of this diagram. So these are like electric field lines. Now suppose the charge has stopped moving suddenly. So there's a very fast deacceleration of the charge, and it comes to rest at x equals 0. So now the charge is at rest at x equals 0. Okay. So how would the electric field lines look like? So for example, forget the outer regions. Now in the inner part, the electric field lines will just be radial. It is just similar as an electrostatic, a Coulomb problem, where the electric field lines are radial and falling off as 1 by r squared. However, for the points at the outer edges, where the information that the fact that the charge has decelerated has not reached yet, they will still think that the charge is still traveling. So the electric field at the outer regions will still point towards the current virtual location of the charge, or as if the charge was still traveling. So the electric field at these locations would point to, say, for example, this point, where the charge's location would have been had it not been decelerated. So of course, there is a mismatch in the electric field because this information that the charge has stopped will have to travel to this point before the field lines become radial. So essentially what is happening is the field lines are changing with time. And this change in time, this is exactly a propagation of an electromagnetic wave that is passing on the information that the charge has decelerated and stopped here, so that the field line configurations of the outer edges would also change. Okay, so this was a very nice example from Rubiki to show how exactly the field lines will change and the electromagnetic wave is actually propagating outwards and outwards. Here comes the more detailed nitty-gritty parts of it. What is important to again, I will not expect you to understand all of these immediately. But what is important for you at this point is to take away some of the flavors and basics so that we can relate these to some of the expressions I show when I talk about the various physical processes. Detailed derivation of these will, of course, become our full set of lectures at the master's level. Okay, so one thing that we all often use is the power radiated by a given charge that is accelerating. So, as I just said in the previous slide, that there are two terms in the electric expression of the electric field from moving charge. One is the part with the constant velocity, and as you can imagine, if it's a constant velocity, if you go to a frame that is also moving with the charge, the electric field will just be radial. So that's why this has no effect from the accelerating charges. And one is the component of the electric field due to the change in the velocity vector, the acceleration vector. And this is the radiative part of the electric field. Now, we will consider a situation where we are non-relativistic, that is beta is less than 1. So in that case, after some approximations, we can write the radiative part of the electric field in this particular format, and the magnetic field is R cross E radiation. All of this again is computed at the retarded time. The retarded time meaning where the charge would have been at an earlier time, T minus R by C. Now, as we know, the Poynting flux is E cross B, and if we just take the mod square of it, so it's E rad square because B is just R cross E, okay, towards the direction of the arc. And if you can simplify this term here in terms of this angle theta. Theta is the angle between the acceleration vector of the charge and the direction at which you are observing. Okay, so this and theta essentially. So so if we just try to compute, so this is the Poynting flux. So the total energy through a surface area dA is R squared d omega per unit time is delta E by T in this way, and there's a d omega term over here. So power per unit solid. So again, what I'm doing here is writing the area, an elemental area in terms of the solid angle. So from this point to R, the elemental solid angle is d omega subtended by this area. So this area is R squared d omega. Again, very simple geometry. So the total energy per unit time, essentially, that is the definition of Poynting flux times the area. Sorry, somebody had unmuted. I'll again request everybody to keep note not to accidentally unmute yourself to prevent disturbances from other participants. Okay. Yeah, so and the definition of Poynting flux is the amount of energy passing through per unit area per unit time. So if you multiply by the area element dA, then you get energy per unit time. So this is then nothing but Q. So the R squared goes away because there is 1 by R in the expression of the ERAD, or the radiative part of the electric field. So the power per unit solid angle is given in this way, okay, which is dependent on the it's proportional to sine square of theta. And the total power emitted, you integrate over all solid angles and then integrate over this angle theta, is given in this way. And this is called the Larmor's formula. Now, immediately, now you can understand that, for example, the emission from this is not isotropic. Okay, because the power per unit solid angle is dependent on this angle theta. And the total power emitted is proportional to square of the acceleration term. So these are some of the fundamental relations we use. So for example, if we find the acceleration vector for a particular situation, and this is what we'll actually use to infer, to find out, and to use when we find out what is the power emitted in synchrotron or Bremsstrahlung processes. All we need to do is find out what is the acceleration vector, what is the amount of acceleration, for example, and use the Larmor's formula to get the total power emitted, or to get the distribution of the power per unit solid angle. Again, as soon as we start talking about per unit solid angle, if you recall, I had also presented in one of the earlier slides, we are starting to define something related to the intensity. Okay, so power per unit solid angle has this sine square theta term, and this is called the dipole formula because it looks like two lobes. The power is zero along the acceleration vector and maximum perpendicular to the acceleration vector. So this Larmor's formula is pretty powerful because in any given situation, as if you can find out the trajectory of the charges, map out this acceleration vector, you can find out the total power in it. So this is quite powerful. Okay, so I'll go into some of the basics of relativistic transformation, and the reason is because this will be required when I discuss synchrotron emission. I will not dwell too much on this, except the fact that from the basics of the special relativistic transformation, you can derive the velocity transformations, and by taking a ratio of this, you can find the transformation of the angle. So if you're if something is moving at an angle theta prime in the frame k prime, and the frame k prime is moving with respect to you with the velocity v, then the angle theta prime will appear in a different way, and that is given by this transformation. This is very important because this becomes very relevant if you are, say, trying to understand the emission from the point of view of a particle that is moving at very high velocities. Now, forget the dipole pattern that I just said now. Just look at how the emission would change if the particle is moving. So suppose a particle is emitting isotropically in its rest frame. Okay, so this is the isotropic emission. The intensity vectors are all uniform at this point. So I just take half of the emission given by these two lines over here. So half of the emission at one side and the other half on this side. Now, if you just look at the angle transformations and put the theta prime equals to pi by 2 in this formula over here, you will find that the tan theta for a high relativistic case is proportional to c by gamma. So essentially, theta is proportional to 1 by gamma. Sine theta is 1 by gamma. So if the gamma is very large, what will happen is these two lines in the rest frame will get mapped towards the forward direction in this way. So the pi by 2 in the rest frame of that moving object gets mapped into a very small angle of 1 by gamma. So if, say, gamma is 100, so starting from pi by 2, all of this radiation that is there in one half of the solid angle will get mapped into a very small, narrow solid angle that is whose extent is 1 by gamma, or cone of half width 1 by gamma. So what this means is half of the energy radiated is being mapped into a very small cone. So essentially the radiation is then called beamed along the direction of motion of the particle. You will find that it's not that the other half is there. All the other vectors are also mapped very close towards the forward direction. Okay, so this is the very concept of relativistic beaming, where if a particle is moving, and if the emission its emission vectors in the rest frame gets beamed along the forward direction. Now, the reason why I talked about uniform emission at the beginning was this was easy to understand. In a realistic scenario, you of course will have the dipole pattern. So if I just go to the previous slide, you will have the dipole pattern being emitted by the particle at rest. However, if the particle is moving at very fast speeds, all of this dipole pattern would itself be beamed forward, because, for example, as I said, the emission is maximum at theta equals to pi by 2. But that theta equals to pi by 2 will just be beamed or like squished in the forward direction. And this is what it is. I'll again not go into the details of it because what this requires is a relativistic a generalization of the Larmor's formula, not required for this summer school discussion in this short lecture. But essentially, what I wanted you to take away is how this dipole pattern would change. So, if this is the dipole pattern of the particle, and these are all consistent with be done with the generalization of the Larmor's formula with relativistic speeds. So this is the if this is the dipole pattern in the particle is radiating in its rest frame, but the acceleration of the so essentially what is happening is this is the acceleration vector, and suppose the particle is moving in a direction along its acceleration vector. In that case, for somebody at rest in the lab, they will see that the dipole lobes would be beamed in the forward direction. Again, the peak of these dipoles will be separated by an angle of 1 by gamma. The other possibility, if the acceleration vector is perpendicular to the direction of motion of the particle. This can happen, for example, if you have the particle moving in a circular orbit, then the direction of motion is perpendicular to the acceleration vector. In that case, the dipole pattern is of course perpendicular to the acceleration vector, but parallel to the direction of the motion of the particle. So what will happen is this lobe of one of the lobe of the dipole will get stretched, but the other lobe of the dipole will get again squished. So you will have a lobe structure of the dipole emission pattern like this. In either case, the emission is beamed along a direction of 1 by gamma. This is constant. So essentially, what we say is that charged particles moving at very high velocities have a beamed radiation, and the radiation is always beamed along a cone of 1 by gamma. Okay, now I'll go into a bit more details about motion of charges in magnetic fields, which is tending towards the synchrotron derivation. So at this point, I'd like to pause and take 2 or 3 questions if there are any. If you can raise your hand, and I'll see if there are any questions in the chat box. Okay, so Nivedita Chaudhary has a question. So how could the two lobes mean the existence of dipole? What does it mean physically? So it's not about some meaning physically. What these lobes mean is there are no lobes that is actually you can touch. The lobes are just a mathematical way of representing what is the power distribution. So the charge is here. There are no lobes actually sitting on top of the charge. Lobes are just a graphical representation of how the power is distributed as a function of the angle. So the power is maximum at theta equals to pi by 2, 0 at theta equals 0. So if you just map out the distribution of power as a function of angle, it appears as a lobe. So this is just a plot of the power. Bhagwan, please unmute yourself and ask the question. Bhagwan, you have no audio. Although you have raised your hand, I don't see any audio connection for you. So if you have any question, you can write in the chat box. We will not be able to hear you. Okay, so I don't see any other hands raised besides Bhagwan. No, again, Nivedita, I think you're so Nivedita asked for the existence of dipoles within the charges be of opposite sign. So this is not the dipole moment. Okay, so this is not the dipole moment you've studied in your textbooks perhaps. This is just a pattern of the radiation which looks like a dipole antenna. So that is not the dipole moment where you have two charges and that's why you keep a dipole. Yeah, you misunderstood. Okay, Subodh Sarangi, please unmute yourself and ask a question.
Okay, can you hear me?
Yes, go ahead.
Yeah. No, I was just wondering, are you also going to touch upon the physical situations where this type of things are observed? I mean,
Yeah.
some observables, yeah, where we do really observe kind of radiation. You are also
Yes.
going to touch
So
upon that.
I will discuss in the remaining half of this lecture one of the physical processes, the synchrotron emission, and then next lecture I will discuss Bremsstrahlung emission. I will not go into Compton scattering for this series.
Okay, okay, thank you.
Dibakar Datta, perhaps the last question.
Sir, the dipole kind of pattern which is forming, is it because the charge is moving? So that's why one place is having less amount of charge, which is it because of the movement of the charge? We are having this kind
I
of
did not exactly catch the whole question, but let me summarize what I understood from the question. You're asking is the dipole pattern that is happening, is it because of the motion of the charge? Again, I think there is a misunderstanding or confusion amongst some of you. The dipole pattern is just how the radiation is distributed as a function of angle. This is not the dipole moment. And of course, the fact that you have radiation from the charge is because the charge is moving. And it's not just charge is moving, the charge is accelerating. So if I again, let me go back to the dipole slide. Okay. So what this means is you have d double dot. D double dot is a displacement vector. It's a double derivative of the displacement vector. Okay, but essentially this is the acceleration vector. So the fact that the charge is accelerating along this particular direction, so that is giving out radiation, and the expression of the radiation is given. The electric field is given like this, or the energy per unit time is given like this. So the dipole pattern that we are saying here, or the two lobe patterns, is just a graphical representation of what the intensity distribution or the power distribution would be as a function of angles. There are no physical dipoles here. Okay, so I will stop now and then continue with the lectures. If you have any other questions, you can write in the chat box of the Google Slides. I'll come back to it later. So now, what are the direct applications of whatever we've learned so far? So what have we learned? We have learned that if the charge is moving and if the charge is accelerating, then the moving charge gives out an electric field that will propagate with time to a large distance. So the electric field has two components. One is 1 by r squared. That is a near field component to the charge. So that is a component of the electric field close to the charge, and it's falling off very fast. So any Poynting flux due to that component will die off with distance. So as you go very far from the charge, you will not feel that part of the electric field. However, the electric field also has a term that is varying as 1 by r, and that is the radiative part of the electric field. And that carries information about the charge to large distances through electromagnetic radiation. And so essentially what it means is the power from the charge can be radiated to large distances. Okay. So, and also we also learned that if the charge is accelerating, then it gives out radiation. And if the charge is moving, then the radiation from the charge will be beamed along the direction of motion of the charge. So one of the direct applications of this is a charge gyrating along a magnetic field. And we will also consider the fact that the charge is the velocity of the or motion of the charge is relativistic. So the charge can be moving very fast while circulating around the magnetic field. So what these equations that I present here are very straightforward generalization of the standard equations of circular charges and gyrating around magnetic field. So this is the force equation, and we all know that this is QV cross B. If you just consider the fact that the particle can be moving with relativistic speeds, we'll have an additional gamma term over here. Again, I'll not go into the details of the generalization itself because I won't have time to cover everything. But the fact that the particle is before the radiation takes place, the particle is not doing any work because it's just moving in a circular path. The gamma will be constant. Let's not focus on the radiation part first. So then this is some standard expressions of the Larmor frequency, which is the QB by gamma MC. For a non-relativistic case, you just have QB by MC. and you have the Larmor radius. Okay. So these are the standard derivations. So these are not just definitions. What is important from here is identifying the acceleration vector. As I just said, if you can identify the acceleration vector, you're done. You can now then compute the total power being emitted. So for this particular system, we don't have any component of the velocity parallel to the charge changing with time. However, we have a perpendicular component of the acceleration vector, or the acceleration vector that is perpendicular to the velocity of the charge. So dv perpendicular dt is q by gamma mcv perpendicular cross v. So the general or the special relativistic form of the Larmor's formula looks something like this. This is something that I have not discussed. The derivation requires some arguments about the relativistic transformation and writing out the Larmor formula in a covariant form. I cannot discuss everything in this lecture, but you have to take my word for it that this is the expression of the Larmor formula for a relativistically moving charge. But a perpendicular and a parallel are the components of the acceleration vector parallel and perpendicular to the charge velocity. Now, in this particular situation, as I said, a perpendicular is 0, so we'll drop this. And what we have only is the contribution from the a parallel is 0, and a perpendicular is the only one that is contributing to it. So we have an expression for a perpendicular here. We'll just put it here. And we immediately get an expression of the total power being emitted by a charge that is gyrating very fast along a magnetic field. And this is how it looks. So R0 is just a classical electron radius. It's just a collection of different constants. Let's not focus on that. What is important to take away from this particular relation is the power being emitted by that particular electron that is moving around the magnetic field is proportional to the gamma square of the electron. So if the electron energy is gamma mc square, MEC square, then it's proportional to square of the energy of the electron. And it is also proportional to square of the magnetic field. There is a beta perpendicular square term here, but beta perpendicular is not relevant because anyway the particles are usually relativistic, so this is just one. So all these front factors are constant, but what you must remember is the power is proportional to square of the energy and square of the magnetic field. So if the magnetic field increases by 2 times, the particles will radiate at a level of 4 times its previous value. This is very important. This is because what you have here. So I'll explain the typical scenarios where this takes place. Suppose you have charged electrons or charged particles or electrons in a particular region of space, and space is always usually filled with magnetic fields at some level. Some regions have very high magnetic fields, some regions have low magnetic fields. Magnetic fields are always there. Now, if these particles become energetic or gain some energy due to some physical process, such that they become relativistic, and then they have a gamma of say 10 or 100, they will start emitting radiation. And the amount of power emitted by that particle is proportional to the gamma square and V square. And the fact that this is proportional to gamma squared has very important implications on the spectrum that we see from this particular system. I'll come to that later on. Okay, so one more thing is what we saw in the previous expression was the fact that this expression is proportional to beta perpendicular square. So I said that beta can be neglected, but there is an important thing, and that one must note is this is proportional to the perpendicular component of the velocity. Perpendicular component being the velocity vector perpendicular to the magnetic field. Okay, that's how the beta perpendicular comes. So if you have a general velocity vector, for example, the charge is not just moving in a circular path, but moving along a helical path. So it has some component along the magnetic field and another component around the magnetic field. Okay, so then what will happen is it will you can make a it will have an angle with respect to the magnetic field. So that is the sine alpha, or the pitch angle of the particle with respect to the magnetic field. So uh, this uh, uh, this expression thus becomes a function of square of the sine of the angle with respect to the magnetic field. Now, this is important again to note. The reason is if the particle's velocity is completely parallel to the magnetic field with no component perpendicular to it, then of course it is not emitting any radiation, at least from this formula. And if that is the case, the particle is just moving along the magnetic field. It has no acceleration vector, or since it's not gyrating. So that is pretty trivial. But although it is pretty trivial, it is important to note that there is a sine square alpha here. And the assumptions on sine square alpha can strongly, drastically change the amount of power being radiated. The reason is if you have an arbitrary distribution of particles, you'll have a wide variations of the angles of the electrons with respect to the magnetic field. So what you need to do is then integrate or find an average expression of the total power emitted. Because if you have so many electrons, each moving with different directions, then some will have different, all of them will have different values of the pitch angle. So to find the mean power emitted by that particular system, we just integrate over the solid angle and divide by 4 pi, and that is how you get this particular expression. So another interesting way of writing this is, again, just for your knowledge, I don't think I'll be discussing this here because I will not be discussing Compton effect, is the fact that the total power emitted by the electron can be written in this particular form, where UB is the energy density in the magnetic field. B squared by 8 pi is the energy density in the magnetic field. So the total power is proportional to gamma squared and the energy in the magnetic field. Similarly, you will find, if you do Compton scattering, you will find that the total power emitted has the exact same formula as the front part, except instead of the energy of the magnetic field, you'll have the energy density of the ambient radiation field. So Compton scattering is when you have, say, these energetic electrons interacting with the background radiation or the photons of the background radiation field. The total power emitted is exactly the same. It's very interesting. Then what we write in that situation is the total power from that particular electron is a joint emission of both synchrotron as well as Compton, where we write UB plus U radiation. In typical situation, the radiation is due to the background cosmic microwave background, the background CMB. Okay, now let us try to start going towards some of the basics of understanding a bit more in the synchrotron emission in a bit more detail. So what have we learned so far? We've learned what is the power emitted by this moving particles and the total expression of the power. What we'd be more interested in is an expression for the spectrum. Of course, I will not go into the details of it. I will give you some of the glimpses of what is happening and some of the basics of the derivation, and give you the final expression because we will not be able to cover everything. So one interesting concept that one has to keep in mind here is the fact that since the particles are moving at relativistic speeds, the emission from the particles again would be punched in a cone along its direction of motion. So suppose if we have an observer at this point, at this location here, and it is observing the particles as they are gyrating along the magnetic field. So this is, for example, this arc represents one small segment of the path of the circular motion of the particle. So the observer will only see this particle for a short duration of its whole trajectory. Although the particle is gyrating continuously, the observer will only see the particle when the observer's line of sight crosses the forward cone along which the radiation of the particle is beamed. This will not be the case if the particle is non-relativistic. If the particle is non-relativistic, it will emit radiation at all different directions, depending on the dipole pattern, of course. But since the radiation is beamed, all of the radiation is bunched in the forward cone. So the observer only sees a pulse of radiation. So as the particle gyrates and suddenly comes towards the observer, the observer sees a pulse of electric field or electromagnetic radiation. Okay, and this pulse width of the can be found by some arguments to be to occur in this particular form, which is gamma q, the Larmor frequency, and sine alpha. And this is a characteristic. So this is the width of the pulse. 1 by this is a characteristic frequency. So essentially, the fact that you are seeing a pulse of radiation gives you a characteristic frequency of the radiation that you are observing. It's called the critical frequency in the books. And this is and there are some additional coefficients in front for the formal definition, which is 3 by 2 gamma q omega b sine alpha. So this is something that one needs to take away, that for a given particle with a given Lorentz factor, and for a given magnetic field strength, omega b is the Larmor frequency, and if I just go back a few slides, omega b is nothing but qb by gamma mc. Okay, so omega b is proportional to the magnetic field, and the critical frequency so omega b has qb by gamma mc, so this becomes gamma square. So critical frequency again is proportional to the square of the Lorentz factor of the particle and the proportional to the magnetic field. And this defines a characteristic frequency at which you should observe the radiation from the system. For example, if you have a particle that is moving around with a Lorentz factor of 100, that gives with the standard magnetic field, that gives you a given critical frequency. On the other hand, if you have another bunch of particles that is moving with the Lorentz factor of 1000, then the critical, so there's a factor of 10 increase in the Lorentz factor. The critical frequency increases by a factor of 100 because it's gamma squared, the same magnetic field. So usually what we find is not particles that are moving, not all the particles move with the same energy. We have a distribution of particles with distribution of energies, and all of these will have their own critical frequency. So sum of all of this contribution then gives you the final spectrum. But for the spectrum from a given electron is always defined by its critical frequency. And as I will show in the next few slides when I show the full spectrum, the synchrotron spectrum peaks at a few factor of the critical frequency. Now, this is how we actually derive the full expression of the synchrotronics, and I will not certainly go into it. It's extremely complicated to be explained in a few minutes. But essentially, I wanted to give you a flavor of the mathematics involved here and what we actually do. So, for example, again, the basic formalism or the basic idea is to identify the acceleration vector. Once you identify the acceleration vector, calculate everything at retarded time, you can get the full expression of the power being emitted. So the particle in this case is, so these are my lecture notes from a more advanced course, so I will not, of course, go into the details of it. But what we do is we identify the move or the trajectory of the particle as it is moving along this arc, and then find the components of the acceleration vector, and then find what if n is the direction of the observer, we find what is the amount of radiation that is going towards that particular direction, and then use the standard expressions of the electromagnetic field. Okay, before I go into this slide, actually I should have. Okay, maybe not. Okay, so what essentially you get after all this is the fact that the total power of the that is being emitted is given by this. Okay, and the spectrum can be written as this and times the function, which is a ratio of the frequency and the critical frequency. Okay, so I'll not go into the details of how we derive this, but this is the expression of the spectrum, and the spectrum looks like something like this. So this function fx, again, this can be derived from the more formal derivation. This was done in the early 1960s, and the expression of the function fx was given by Westfold in 1959. These are called the Westfold integrals. What this function fx looks like is something like this. Again, x is the ratio of the frequency to the critical frequency, and it is related to the Boltzmann to the Bessel's function. X times the integral of the Bessel's function from x to infinity. But what is important for you to notice this is the expression of the power on expression of the spectrum, and this is the fx function. The peak of the fx function is at 0.29x, or that is at a frequency that is 0.29 times the critical frequency. Now, this is the expression of power for one single particle. So that particle will be emitting radiation over a wide range of frequencies, but the peak of that frequency would be at the critical frequency. And again, if I just go back to what I discussed, the fact that we have a critical frequency is essentially related to the fact that we are seeing a pulse of radiation, not seeing the entire, the entire gyro orbit, but we're just seeing a pulse of the radiation. And that gives you defines a characteristic frequency, the critical frequency. So this is how the power or the spectrum of the synchrotron emission looks for a given particle, for a single particle system. Now, as I just said, you will have a distribution of particles with a wide range of energies. Usually, in such case, in systems where we have energetic electrons, it is usually found that the electrons are distributed as a power law, where the energy distribution of the electrons can be mapped as e to the power minus p. P is a power law index of the electrons times dE. So this gives you the energy distribution or a spectrum of the electrons in this space. To find out the total power emitted by the system, all we need to do is take the power or the spectrum emitted by a single electron and thus integrate over this distribution of electrons or a power law distribution. So what we do is we take the previous expression of that we get for the spectrum p omega, and then integrate over this distribution. And after some mathematical jugglery, we will find that we can separate this out into two parts. One that is proportional to the frequency that is being observed, that is omega, and that is to the power minus p minus 1 by 2. And then it's just an integral over this fx function. And these integrals can be performed, there are analytical relations to perform this integral. The takeaway message from this is, if you have an inherent power law distribution of an energetic charged particles or electrons, and if the power law distribution of the electrons is p or minus p, then the observed spectrum from those electrons would be minus of p minus 1 by 2. This is very fundamental and powerful. What it implies is, if you now observe synchrotron radiation at different frequencies from a given particular object, with that you can find what is the exponent of the spectrum, because you can map out the power at different frequencies and you eventually will get a power law. You can map out what this p minus 1 by 2 is, and from this you can infer what is the state of the electron energy distribution of that particular region. So if you get the spectrum of the synchrotron, you can immediately get the value of p, and you would then infer that the electrons at that particular location is distributed as a power law with an exponent of p, which I think is very remarkable, that you can infer the physical state of that particular region just by observing the synchrotron emission at different frequencies. And this is just an analytical integrals of how identities of how you can compute this integral that I said, this particular integral over here. This is the full expression of power. I'll perhaps leave you with this image to show what the synchrotron or map of the synchrotron emission looks like. This is the synchrotron emission from a radio jet coming from a supermassive black hole, from galaxy Cygnus A. This is observed at 5 gigahertz, and this is the radio spectrum of Cygnus A. This from observed by LOFAR. LOFAR is a low frequency radio telescope operated by several European countries as a joint venture. So these are the kind of images we actually see when we actually study these things using radio astronomy. So what we infer is there is a thin, if you can, so there are a lot of interesting nuggets in this particular pictures here. So let's focus on this picture first. So you can see there's a bright dot here. This is the galaxy. Okay, so this is the core of the galaxy from which this jet is coming out. And the black hole, a supermassive black hole, resides somewhere here. You can see a thin strip of emission going from here to here. This is a jet of highly relativistic particles that is being coming out from this black hole. And the size of this region is much, much larger than the galaxy itself. So this is very large, several tens of kiloparsec, or I think 100 kiloparsec. I forgot exact size, 60 kiloparsec. There was somebody who unmuted. Yeah. So one thing before I go into this two bright knob here, one thing you will notice is you can see this trail of gas here, but this is much fainter on the other side. And again, this is very typical of radio galaxies where we often do not see the other jet. This is because these particles are moving at relativistic speeds, and if they are aligned towards your line of sight, the emission from these will be boosted due to the relativistic Doppler boosting. While the emission from this, since they are moving away from you, will be deboosted or decreased, again due to the same Doppler relations. So you can see the thin jet. Now jet is going and hitting the ambient gas at these two locations, and this creating these bright spots over here. These are called hotspots. The gas goes, hits the hotspots, and then is coming back down in a large plume. And all of this emission is due to relativistic electrons that are gyrating very fast across the magnetic field over here and giving out synchrotron radiation. And this is how the spectrum looks like. So these are the lobes and the counter lobes, and this is the spectral index map. Of course, different regions have different levels of energetic electrons. And now I must say that if you remember, I told you to focus on the fact that the power of the of a given electron, or the power emitted by a given electron, depends on square of the Lorentz factor, or square of the energy. Now, if you just look at this fact that you have a power law distribution of the energies, so the initial spectrum of the electrons is something like e to the power minus p. Now let's look at the electrons at two different parts of the spectrum. One at the lower end of the spectrum and one at the higher end of the spectrum. Now, starting from an initial power law, if the electrons are losing energy, then the higher energetic electrons which lose power at a much faster rate than the lower energetic electrons. So what will happen is once this group of electrons with an initial power law starts to emit synchrotron radiation, there will be unequal cooling or unequal radiation from different electrons with different energies. So the spectrum will not remain a power law. If the cooling was uniform for all energies, the power law will just shift. But that is not the case. So the nature of the spectrum changes, and higher energetic electrons decay faster in energy because they give out a lot more synchrotron radiation than the lower energy electrons. And this is very much reflected in the spectral maps. If the inherent spectrum of the electron distribution changes, then what we find is these regions below, close to at a much lower. So this is the backflow. So the jet is going, hitting here and coming back. All these electrons in the backflow, these are all old electrons. That is why they have much steeper spectrum, because their energy has decayed. Whereas these electrons at this point, they remain fresh and accelerated and have a much shallower power law. So these are the kind of things that we infer where we identify the steepening of the spectrum to infer what is the initial the inner conditions of the electrons and the age of the population of the electrons. So I think I'll stop here. I'll see if there are any quick questions. Otherwise, you can put them in the Google form. Okay. If you have any questions, raise your hand. I'll see if there are any questions on the chat now. Shweta Bhave asks, is there any significant reason for obtaining dipole-like intensity profile for accelerating charges? No significant reason. That's how it appears mathematically. Power emitted, and so Sanjana Patil asks, and the power emitted is accelerated at high velocity? Question mark. Did not really understand the question. If Sanjana is there, you can unmute and ask the question yourself. Not sure if Sanjana Patil is listening. Any other questions? I don't see any raised hands. So if there are no other questions, then I will stop